Okay, example 3 from 1.2. Really similar to example 2, except the key difference here is if the parameter, or the coefficient, is attached directly onto the x, then it is a horizontal stretch, not a vertical stretch. And that's certainly within the general function form, and we're going to look at that a lot more in 1.3 in detail. So we're going to do this a through b. The one thing I'd like to point out before we go on is that it is a different w. Right, and that's going to be really important as we go through. So to try to make that at least a little bit workable is we're going to do the domain and range for f of x right away. And that is that x exists between -4 and +4 and is any real number. And y exists between 0 and 4 and is any real number. And just to save myself a little bit of a headache, I am going to copy that so I can paste it later. Okay, so letter A here. I'm going to try to keep and be consistent with this, that if we are trying to turn f of x into g of x, then what I am going to do, and I want to identify this, that the b parameter is 2, so there is a horizontal stretch by 1 over 2, which means that the coordinate, any coordinate, x comma y on f of x, is going to turn into 1/2 x comma y on g of x. And it's very important that if the b value is 2, the horizontal stretch is the reciprocal of that b value. And that'll be very consistent throughout. So here is our original w with all of its points. Now, when you are affecting the input, it is very useful to write an additional table of values for g of x. And then really important, if you compare the two table of values, and I scrolled a little far there, that all that's happening to go from this coordinate to this coordinate is my x of -4, so -4 comma 4, turned into -4 times 1/2 comma 4. So the y value was unaffected. The x value got multiplied by 0.5, but the y value didn't get touched. So when we look at the graph of y equals g of x, this w has the same height, but it has a much, condensed width, or a smaller width, I should say. So I'm just going to bring back my domain and range, a little bit messy there for sure, of f of x. And what we're going to do now is we're going to look at g of x. And I ran out of room here a little bit, but I'm going to sneak it in on the right, that if I looked at the domain and range of g of x, and kind of a bad choice there because it's drawn in red. So the domain and range of g of x, we notice that the domain is different. This is now only existing in between -2 and +2. So x exists between -2 and +2, and x is an element of the real. The range, because we only did a horizontal stretch, do not overthink the range. It's unchanged, right? Unless we do some kind of a vertical stretch or later on a vertical translation, then the range will not be affected. Now, important to recognize the connection between the domain of the original and the domain of the transformed is that my x coordinate was multiplied by 1/2. And because that happens to all the coordinates, we can look at how that happens to the endpoints of our domain as well. All right, the next one here is when they put a fraction inside there. And it's really important that we're going to approach this the exact same way. I'm going to say that the b parameter is 1/2. Therefore, it is a horizontal stretch by, and at least once, I would like you to picture that as 1 over 1/2. That's still just 1 over b. But we spent a lot of time talking about that when we divide by a fraction, we multiply the numerator by the reciprocal of the denominator. So this is really a horizontal stretch by 2. So looking at those points on f of x and our transform function g of x, we are doing a horizontal stretch by 2, or taking any coordinate and multiplying the x by 2, by the stretch itself. Now, they condensed this table a little bit, and that's okay. But what they are showing now, and it's a little bit tricky, and I don't really like how they represented it, is they are saying that g of x is 4 if x is equal to -8. Now, the idea behind this is that if I put 4 into f of x, or -4, sorry, into f of x, it gives me 4. But because I would multiply that x by 1/2 first, what that means is that g evaluated at 4 is actually equal to function f evaluated at -8. So that's going to be 1/2 times -8. So when we look at what that ultimately does is it means that our w becomes much more compressed. And that is a tricky thing. I would highly recommend that you use the mapping and focus on that. This is something that a lot of students struggle with initially, and then as we work through it and do more and more, it becomes all the easier, I think, in the long run. So I'm going to do the same thing I did on the previous question. if I can hit it. I am going to paste my f of x domain and range in again, because that hasn't changed. That's the original. But now when I look at g of x, and we'll do that in red, my domain has changed again. So if we look at my domain, I would have that x exists from -8 to +8. That's the original x values multiplied by 2, and x is an element to the real. And my new range is exactly the same because we haven't done any type of vertical stretch. Now, I did forget this on the last question, but fortunately, it is the same for both. And I am going to write in a nice kind of general statement that's always true, is that if you only do a horizontal stretch, then our y-intercepts are invariant. Now, the reason we can get away with saying this, and it's a universal truth, is that every single y-intercept has an x value of 0 and whatever y value it needs to be. Well, if I'm multiplying x values by anything, this 0 is going to stay at 0. So for this particular question, that y-intercept 0, 2, and I'll label that or highlight that on the graph, it's right here, that stayed invariant. Not only is it present on both the graphs, it is an invariant point. And I want to reiterate that this and this, the intersections, are not invariant. They're just kind of coincidental intersections of the original and the transformed function.